In the previous video, we regarded a vector v in Minkowski space and discussed how it may be expressed using any set of basis vectors. The expression for v with a particular set of basis vectors is completely specified by the vector components v mu or v mu prime, depending on the basis. The inner product between two vectors may be expressed using these vector components and knowledge about the inner product between the basis vectors, given by the metric tensor eta. There is nothing special about the unprimed system, and we may do the same in the primed system with the same result, but in terms of the primed components. To write this without the metric tensor, we can introduce a different set of vector components with lowered indices by including the metric tensor. The same again goes for the primed system. Vector components with upper indices are called contravariant vector components, while those with lower indices are called covariant vector components. We may now rewrite the inner product as a sum of covariant vector components multiplied by contravariant vector components. Since the metric is symmetric, it does not matter which vector we write with contravariant or covariant components as long as we have one of each. Let us examine how the vector components in different bases relate to each other. We will mainly use the fact that the vector itself is independent of the basis used to describe it. We call this relation star. We know from before that the relation between the bases is given by E mu is equal to lambda mu prime mu E prime mu prime. Since the vector must be the same regardless of the basis, we can start from the expression in unprimed basis, write the unprimed basis vector in terms of the primed ones, and using the star relation. Since the basis vectors are linearly independent, these two coefficients must be the same, and we find that v mu prime is equal to lambda mu prime mu v mu. This is called a contravariant transformation due to the fact that the coefficients v mu transform in the opposite way from the basis vectors. Remember that in the transformation of the basis, the primed basis vector appeared at the same side as the lambda, and the primed indices were summed over, while the opposite is true for the contravariant vector components. If we instead look at the covariant vector components, we can write down the relation to the contravariant components in the primed basis. Multiplying by lambda mu prime mu, using the transformation property of the contravariant components, and that the Lorentz transformations preserve the metric tensor, we find that this is equal to eta mu nu multiplied by the unprimed contravariant components. This relates the covariant vector components of the different bases as v mu is equal to lambda mu prime mu v mu prime. Note that the primed indices are summed over here, as was the case for the basis vectors. The covariant components therefore transform as the basis, which is the reason for calling them covariant. Let us look at a particular vector, the position vector in Minkowski space, which describes an event, that is, a time and a position. We will here and in the future be using the notation ct is equal to x0 for the time coordinates. As for any vector, the position vector may be rewritten in terms of either vector basis. The Lorentz transformation relates the primed coordinates to the unprimed ones with the transformation coefficients lambda, and differentiating this relation with respect to x mu, we find that lambda mu prime mu is simply the partial derivative of x mu prime with respect to x mu. If we multiply lambda mu prime nu by the opposite partial derivative, that of x mu with respect to x nu prime, we can use the chain rule to deduce that this must be equal to 1 if mu is equal to nu and 0 otherwise. We write this in terms of a delta. This means that dx mu prime is the inverse of lambda mu prime nu. We will denote this as lambda mu nu prime. Note that the primed index appears as a subindex in the inverse transformation and an upper index in the transformation. In the same way, we can relate the sum of the unprimed indices in the transformation lambda and its inverse, ending up with a delta in the primed indices. This provides us with an alternative way of writing the transformation rule for covariant vector components. Multiplying the transformation rule by lambda mu nu prime, and using the fact that this is the inverse of lambda mu prime mu, we find that this is equal to the primed covariant vector component. To summarize, we have expressed the primed vector components, both co- and contravariant, in terms of the unprimed ones, using the transformation coefficients lambda mu prime mu and their inverse. In the next video, we will be discussing how this relates to more general tensors in Minkowski space.